This is Stacy Spitzer, Zach Compton, Sylvia Flores, and Marissa Smith discussing female rats are more susceptible to the deleterious effects of paradoxical sleep deprivation on cognitive performance, written by Vahid Hajali and his colleagues. Paradoxical sleep is characterized by rapid eye movements, inhibition of muscle formations, and is recognized through EEGs as having great activity in the forebrain and midbrain. Because this stage of sleep occurs more frequently toward the end of the sleep cycle, people in today's society are having problems with paradoxical sleep deprivation, or PSD, that are most likely self-induced. This lack of sleep is linked to other health issues, including memory formation and anxiety-like behavior, which will be analyzed in this paper. Memory consolidation is believed to occur during paradoxical sleep, as seen by activity in the hippocampus during this stage. There are also sex differences in sleeping patterns. Research shows that females are more likely to have sleep difficulties, such as insomnia. In addition to simply having sleep difficulties, females are more likely to feel its effects following the sleep deprivation. Thus, this paper discusses the differences in the effects of PSD between males and females, specifically in rats. The subjects in this experiment were adult male and female Wistar rats aged 3 to 4 months. The three groups used in the study were male rats, intact females, those with ovaries, and OVX or ovariectomized female rats. The OVX rats had their own ovaries removed in order to reduce hormonal influence from their reproductive cycles. 4 rats in the same group were placed in a multiple platform model where they could move freely. Because of the muscle tone loss in PSD, the rats would fall into the water and be awoken during paradoxical sleep stage. The Morris water maze, shown below, consisted of a circular pool that was divided into 4 equal-sized quadrants. There was one square platform that led to an escape route in the northeast quadrant. Each wall in the maze had different shapes to differentiate between locations. After 3 hours of training, the sleep-deprived rats were individually placed in the maze, and their time to reach the escape route was recorded. Spatial memory was tested when the platform, which consisted of the escape route, was removed. The time and distance spent in the northeast quadrant was recorded. An open field test was then performed 10 minutes after the PSD period to determine the rat's anxiety and behavior. The rat's rearing and time spent in the middle of the field were indicative of its behavior and anxiety. Analysis for the data collected included MWM probe trials, swim speed, open field testing, and corticosterone levels. These graphs show the effect of PSD on spatial learning, or learning where the escape route was, in A, male rats, B, intact female rats, C, OVX female rats, and D was a combination of all 3 groups for comparison. The last graph shows that the OVX were the most significantly impaired group with respect to spatial learning, as shown by less decreasing in the time it took to reach the escape route after deprivation of paradoxical sleep. The results for the effect on PSD on spatial short-term memory as it relates to the water maze test are shown in the next 4 graphs. Again, graph A shows the results for male rats, B for intact female rats, C for OVX female rats, and D was a comparison. From these 3 graphs, it is shown that the PSD intact and PSD ovariectomized female rats spent less time in the northeast target quadrant. Male rats did not show a decrease in the time spent in the 4th quadrant following PSD. These last 3 graphs depict the effect of PSD on anxiety-like behavior and locomotive activity. As shown in the first graph, PSD increased the anxiety-like behavior, or time spent in the inner region of the field, in all 3 groups of rats. Graph B shows the total distance moved in the open field, indicative of exploratory and locomotive behaviors. PSD had no effects on these behaviors for all 3 experimental groups. Lastly, graph C shows the number of rearing in the rats. In this case, PSD did have an effect on anxiety-like behavior, decreasing these numbers. However, like graph A, the PSD effects on all 3 experimental groups were the same. This table includes the weight change and corticosterone levels in the rats before and after PSD. While there were no significant changes in the body weight in post-PSD males, there were significant weight changes in both the intact and OVX females after PSD. This demonstrates that there may be an aversive effect of sleep deprivation on induced body weight loss. Corticosterone levels for all 3 groups were not affected by PSD. This study was conducted in the hopes to determine the negative effects of PSD in the areas of spatial learning, short-term memory, and anxiety-like behavior in male and female rats. These tests determined that OVX female rats' spatial memory was severely worsened than that of the male rats. Observing that there were no significant effects on mood, motivation, or sensory motor coordination, which is shown through the previous table of swimming speeds, it can be reasonably determined that PSD worsens the spatial learning and memory due to the deleterious effects on brain regions involved in memory consolidation, such as the hippocampus, which partially occurs during the paradoxical sleep stage. While this experiment studied the effects of PSD, there are adverse consequences on cognitive behavior no matter the method of sleep deprivation. The stress levels in the rats as it relates to cognitive impairment were a big part of the experiment. The corticosterone test performed during this experiment, however, showed no major difference in the stress levels of the tested rats and the control rats. It has also been discovered that the removal of the adrenal glands in rats did not prevent them from SD memory problems. This discovery reduces the role of stress on the deficits in memory loss. The study also points out the differences in the reactions of male and female rats during PSD. While it is not yet known what causes these differences, it is suggested that they are related to sexual dimorphism in brain organization and function, in which male and female brains consist of different neurotransmitter systems and neuroendocrine regulation. For example, the OVX female rats had no estrogen, which has been documented to prevent against neural injury or deleterious effects. Future research could consist of using different breeds of rats, such as Zucker rats or Long Evans rats. Improvements to this experiment could be to separate the rats by sex during group testing. This would reduce any hormonal stress between male and female rats that could occur. Lastly, the rats of various ages could be used. These differences in ages could show how sleep patterns differ amongst ages, leading to differences in sleep deprivation among rats.